Hi everyone. Thank you all for taking the time to watch my thesis defense on the data-driven modeling of dynamical systems. About 5 years ago, when I started my PhD, one of the most exciting things in the world to me was the SpaceX Falcon 9 rocket going up into orbit, deploying a payload, and then autonomously navigating itself back to a pinpoint target. Around the same time, DeepMind's AlphaGo was a game-playing AI that beat the world champion at the game of Go, an AI achievement that experts thought was decades away. Since then, we've seen autonomous decision systems make their way into self-driving cars, rovers that explore Mars for us, and even attempts at epidemic quarantine zoning. One of my favorite theories of cognition comes from Thinking Fast and Slow by Daniel Kahneman, where he essentially talks about two different modes of decision making. One mode of decision making is the planning mode, or the slow mode, where we perform model-based decision making. Imagine you have this agent and it's faced with the decision of pressing the red or the green button. It might use a model of itself in the world to predict that if it presses the red button, it would take it to an unfavorable state and therefore decide to press the green button. Sometimes you may not have time to do this sort of deliberation, such as if you're playing tennis and need to make a split-second decision. Over here, we rely on intuition, fast thinking, or model-free decision-making. In the model-based decision-making paradigm, we typically describe the dynamical system of interest as well as its environment with a state called x sub t, as well as the control inputs into the system as u sub t. So in this case, the control inputs are going to be the thrust and the direction of the thrust of this rocket. We then make use of a dynamics model, which is a function that takes as its inputs the current state of the system as well as the control inputs and predicts a distribution over the next state of the system at some time in the future, t plus 1. We also make use of a reward model. This is a function that maps the state and the control input to some notion of reward. So the goal state would presumably be a state where the rocket is safely back on the ground and would have a high positive reward. And if the rocket were to find itself crashed into the ground, that would have a low negative reward. So with these two models, we can perform optimization in order to figure out the best sequence of control inputs to be able to navigate us through favorable states. Sometimes we don't have time to do this sort of deliberation, and so instead rely on something called a policy. A policy is a function that directly maps the perceived state of the world to a control input. And oftentimes, this sort of a policy is represented by something like a neural network. So in each of these paradigms, there are functions we don't know. In the model-based paradigm, we may not know the dynamics function and we may not know the reward function. And in the model-free paradigm, we may not know the optimal policy. So the first thing that we would do is parameterize each of these functions. So we would choose a functional form that can express the function of interest. If we know nothing about it, that might be a neural network, or it could be something more structured if we have some prior knowledge. We then go and gather some data. So this is going to be data of the form state, control input, and the associated reward as the agent interacts with the environment. Then we will perform some form of machine learning in order to infer the relevant models of interest. In the model-based framework, this is typically called system identification. In the model-free framework, we typically call this imitation learning if the data set was given to us by some form of an expert, or we call this reinforcement learning if the agent goes out and collects the data set for themselves. So there are real-world challenges to doing this sort of identification. The first is of parameterization. How do we choose these functions that are going to repress the models of interest? And how do we choose them in a way so that we can train them with limited data but have them be accurate? Then there is always a challenge of hidden states. So most dynamical systems are not fully observable. For example, in aerospace settings, we cannot directly observe the momentum in the fluid behind the vehicle, even though it might be relevant to being able to predict the dynamics. And so we need to perform identification in partially observed settings. There's also the question of how to get the data, so data acquisition. How do we safely collect the data set that we're going to learn from? And then there's always a challenge of poor data quality. Anyone trying to work with today's COVID-19 data will realize that there is not only a lot of noise, but systematic biases from a lack of testing that make the data difficult to work with. So my contributions are in each of these areas. On the question of how to parameterize models, we studied the parameterization of the dynamics model and tried to inform the model with physics-informed priors so as to create a function class that learns from limited data, but effectively. This is something that we had accepted to L4DC in 2020. And then on the problem of hidden states, we tried to present a scalable identification for nonlinear and partially observed dynamical systems. And the algorithm that we presented was accepted to ICML in 2020. On the question of data acquisition, we studied the problem of safe and online learning from demonstration and presented an algorithm called Ensemble Dagger that tells you how to share control between a novice and an expert in order to train the novice. And this is something that was accepted by IROS in 2019. And then on the question of poor data quality, we actually did a case study of trying to fit reactive models of COVID-19 to the available data. And this is something that is under review at Nature Scientific Reports. So I will be focusing on the first two of these contributions for the majority of this talk, and briefly touch on the other two contributions later in the talk. So let's dive into the question of parameterization. I'm going to be talking about structured mechanical models for robot learning and control. This was a joint work with Jayesh Gupta, and it was advised by Professors Manchester and Kokendorfer, and it was accepted by L4DC in 2020. So we're returning to the question of choosing a model class. So like I said, we need a dynamics model in order to do model-based decision making that tells you what the next state of the system is going to be given the current state and input. So we can ask the questions, what kind of function is this and what parameters does it depend on? We want to choose a function class that is going to accurately reflect the real world, but also be trainable with limited amounts of data. So the first thing that we could try to do is derive this model from first principles. Going back to our introductory physics classes, we might draw a free body diagram of the system, characterize all the forces that might be acting on the system, and try to use F equals ma to figure out the acceleration on the system. So when I talk about the dynamics of a system, I essentially mean being able to predict its accelerations as a function of its configurations, its velocities, and the control inputs. So if we go and derive this model from first principles, one of the benefits is that it's going to be data efficient. So it typically doesn't have that many free parameters that you need to go and fit to data. But sometimes the textbook models that we use may not be reflective of the real world. This is very common when you work with turbulence or friction. So in order to be able to capture what we see in the real world, we might opt to use a black box neural network. This is going to be a neural network that simply takes the configuration of the system Q, the velocities on the system Q dot, as well as the control inputs U, and try to directly map them to the accelerations that we're interested in. So this has expressive power. Because we're using a neural network, it could hypothetically express any function of interest, but it has a lot of model variance. So it is quite expensive to gather data on a real physical system, and typically we need more data than we can gather in order to accurately fit a neural network. So we ask, can we get both data efficiency and flexibility from one model class? And so we present structured mechanical models. So to introduce this concept, we're going to do a little bit of a background on Lagrangian mechanics. So here is a system. This is a simple spring mass system. And Lagrangian mechanics says that you can derive the dynamics of the system, that is, predict the accelerations of the system, by specifying the energies of the system and the forces that act on it. So over here, there are two energy terms. One is called the potential energy and is the energy stored by the spring in this case. There's also the kinetic energy, which is the familiar 1/2 mv squared term, and is the energy inherent in a system that is in motion. And then there are generalized forces. This captures all the external forces that act on the system. So for example, there could be a control input driving the system, and there could also be friction or air resistance that are resisting the system's motion. So the first thing that we would do is define something called the Lagrangian, which is simply the difference between the kinetic energy and the potential energy of the system. We can then relate the Lagrangian of the system to the generalized forces using an equation called the Euler-Lagrange equation. And this is a very elegant equation that if we just apply chain rule to, we can end up with the equations of motion, or the accelerations on the system. So structured mechanical models simply decide to, instead of directly predict acceleration with neural networks, use neural networks to parameterize the components of the Lagrangian. So specifically, let's go back to exactly what the Lagrangian is. It is the difference between the kinetic energy and the potential energy of the system. And the two unknown quantities over here are this mass matrix, M, and the scalar potential field, V. And so the first thing that we would do is parameterize these unknown quantities and try to learn them with neural networks. So we have one neural network, which takes the configuration of the system, which is Q, and maps it to a positive definite matrix, which is the mass matrix, M. We have another neural network mapping the configuration Q over to a scalar potential V. So the first two neural networks that make up a structured mechanical model are the two neural networks that make up the Lagrangian of the system. Now let's focus on the generalized forces. In the general case, we may not know anything about these forces, and so we just have a single neural network mapping us from the configuration Q, the velocities Q dot, and the control inputs U over to the forces that act on the system. So these are three neural networks, and this gives you a full description of a structured mechanical model. From these three neural networks, we could go about and try to compute accelerations. But in many cases, most robotic systems are actually control affine. So there is a little bit of structure to the generalized forces. In particular, we can safely assume that the control inputs map to forces through something called a control input Jacobian, which is B. And so we can use one neural network to predict the control input Jacobian, and then capture all the other forces like friction and air resistance with some sort of residual forces. And that is going to be just a function of Q and Q dot. So this structure can buy us some data efficiency, and typically is general enough to capture many robotic systems of interest. So this is a special case of a control affine system. But let's say we've parameterized both the Lagrangian and the generalized forces. How do we now predict the accelerations on the system? So to do that, we're going to turn back to the Euler-Lagrange equation. And by applying chain rule to this equation, we end up with another equation called the manipulator equation. And this is just the second order differential equation that we are much more familiar with. And in this differential equation appears a term called the Coriolis forces. So the Coriolis forces are simply forces that arise from the gradients of the mass matrix with respect to the configuration. But we can just shift that equation around and isolate the quantity of interest, which is the accelerations, Q double dot. And what we'll notice is that this actually just looks like acceleration is equal to force divided by mass, or F equals ma. So the Euler-Lagrange equation allows us to go from these neural networks that we've parameterized to essentially F equals ma. So a quick summary of what we talked about here. Instead of the black box neural network, which directly tries to predict accelerations as a function of these three inputs, the configuration, the velocity, and the control inputs, instead we parameterize the components of a Lagrangian description of the system, and then we use the manipulator equation, or Euler-Lagrange equation, in order to predict the accelerations, Q double dot. So let's quickly talk about expressive power. Does a structured mechanical model, is it able to express the same set of functions a black box neural network can, or are we introducing some degree of bias when we use them? This is a question that we seek to answer. And so specifically, we ask, can a black box neural network and a structured mechanical model express the same set of functions? And the answer is that yes, a structured mechanical model can express all the functions that a black box neural network can express. And it's fairly easy to see this from the manipulator equation. So in the manipulator equation, let's assume that the mass matrix were to just learn the identity mapping. If it were to learn the identity mapping, it turns out that the Coriolis forces, which depend on the gradients of the mass matrix with respect to the to the configuration, are going to end up being 0. Similarly, the scalar potential field can be learned to be a constant, and so its gradients will also go to 0. And what we are left with is simply that the accelerations in the system will be equal to the generalized forces that act on it, which is, in the general case, just characterized using a black box neural network. So we showed that a structured mechanical model can actually express everything a black box neural network can express. So why should we expect any data efficiency by using a structured mechanical model? Right? Conventional learning theory would suggest that if you use a more expressive function class or equally expressive function class, then it should have about the same model variance. Well, we look at inductive biases from the perspective that Andrew Wilson used to study inductive biases of convolutional neural networks. So the idea here is essentially, imagine we have three different data sets. We have a data set of a manipulator that is generated with friction, right? So imagine that we go out into the real world and collect some manipulator data. We can also get a robotic manipulator that is simulated on a computer, so it doesn't have any friction. And then imagine we have a data set just of random noise. So if we derived our manipulator equations from first principles, well, there would be a model in the model class that is consistent with the manipulator without friction, right? We can calibrate its parameters, and there is a model in the model class that can explain that data set. However, that model class does not have support for a manipulator with real-world friction or random noise, right? There's simply no model in the model class that can express the data we're giving it, right? And this is what bias is, strict bias. On the other hand, a black box neural network, there is something in the model class. There is some neural network that can express all of these data sets. The problem is that a black box neural network doesn't know a priori that we are interested in manipulators and not in fitting random noise, right? And as a result, we need a lot of data in order to convince a black box neural network to express functions that are more consistent with manipulator dynamics than just functions that look like random noise. So our hypothesis is that a structured mechanical model essentially reweights the different data sets that it's expecting to see, even though it can express all of them. So a structured mechanical model, because of the way we've constructed it, just expects that it's going to be seeing a manipulator with or without friction much more than it is random noise. So it can still express everything that a black box neural network is. It just has a prior belief that it's going to see data sets of a certain kind. So this is where we expect data efficiency to come from, right? Despite the fact that they have the same expressive power. And so in our experiments, we compare these two methodologies side by side to see how well they generalize from limited amounts of data. Specifically, we're going to look at a control affine version of a structured mechanical model because almost all robotic systems can be assumed safely to be control affine, or many robotic systems at the very least. And so what we do is we went and collected data from a variety of different robotic domains, and then trained each of these model classes with limited amounts of data, ranging from 256 training examples to 32,000 training examples. And we look at the validation error. So this is on a test set of data that the models haven't seen. How well are they able to correctly predict the accelerations? As one would expect, the more training data you give it, the lower your validation error. But what we can see is that a structured mechanical model has orders of magnitude better validation errors than a black box neural network. So I would much rather use a structured mechanical model to fit to limited data than a black box neural network, is the takeaway here. And now we can ask another question. So what if we were to take two models that have comparable validation errors? So imagine we gave a structured mechanical model 2,000 data points in order to train. And so that would have comparable model accuracy to a black box neural network given 32,000 training examples. So imagine we've controlled for validation error. Well, now we could try to use these for optimal control tasks. And we would assume that because they have similar validation errors, they're both equally accurate in predicting dynamics. So they should do equally well in optimal control. But what we find is that despite controlling for validation error, a structured mechanical model is still better for optimal control tasks. And this naturally begs the question, why? And what we actually found is that a structured mechanical model is much more accurate at predicting the Jacobians of accelerations in unseen states than a black box neural network is. So despite being similar in terms of their ability to predict accelerations, a structured mechanical model is more accurate when it comes to predicting the Jacobians of those accelerations, which are really important for optimal control. So the takeaway here is firstly that the variance of neural networks can be greatly mitigated by enforcing appropriate priors, and that structured mechanical models are an appropriate prior for physical dynamics. Okay, so now let's turn to the question of hidden states. So what I'm going to present is the scalable identification of partially observed systems using certainty equivalent expectation maximization. This was a joint work with Jean, Jayesh, and it was advised by Professors Crow, Manchester, and Kokendorfer, and it was accepted by ICML in 2020. So hidden states are a common challenge when you work with almost all real-world data sets. In the COVID-19 pandemic, the hidden states that we often encounter are the true number of people that are infected in a given population and the true number of people that might have recovered from the disease, and probably also the amount of social distancing that is actually being followed. In aerodynamic systems, the hidden states are going to be the fluid states, so the momentum that is in the fluid behind the vehicle that are going to affect its dynamics, but is something that we cannot directly observe. Also, the temperature of the actuators is also very relevant to predicting the dynamics accurately, but is something we may not have sensors measuring. For financial time series, imagine we're interested in trying to predict the value of a given company. We would want access to its cash flows, to its demand, to its supply, but these may not be something that we have access to, and instead we may only have access to a couple of financial statements that are few and far between. So the problem statement over here is, imagine we have a dynamical system with a state X that evolves over time, but that state is hidden from us. Instead, what we have access to is an observation called Y, and the control input that we drive the system with. So what we're interested in doing is system identification. So we're interested in fitting a model F that predicts how the hidden state is going to evolve over time, and another model G that predicts how the hidden state emits the observation that we saw. So a little bit more specifically, given a time series of observations, which we call Y1 to T, and a time series of control inputs, which we call U1 to T, and some sort of parameterized model. So imagine that F maps the current state and input to the next state, and G maps the current state and input to the observation that we saw. Well, actually assume that they are stochastic models. So imagine we're adding some process noise, which we call W, to the dynamics model, as well as some observation noise V, which we add to the observation model. What we're interested in doing is finding the likelihood maximizing set of parameters. So we want to find the set of parameters that maximize the likelihood of the time series of observations that we saw. However, in order to actually, we can't directly compute this likelihood. We need to reason about what those hidden states were. And specifically, we need to marginalize them out. Right? So in order to do this tractably, there's an algorithm called expectation maximization. And expectation maximization essentially says, well, let's just start with some guess about what the dynamics of the system are. Well, we can use that guess of what the dynamics are, as well as the time series of observations, in order to infer what the hidden states could have been. Right? Specifically, what we're interested in doing is computing the posterior distribution over hidden states given the observations and the current guess of the system dynamics. So we can use that posterior distribution to essentially pretend like this is now a problem of complete information. So we can try to compute this integral by essentially sampling from this distribution, this posterior distribution that we've characterized. And now we can define the joint log likelihood over states and observations. And we can try to maximize this quantity in order to make an improvement to the model. And if we iterate these two steps, the E step and the M step, we are going to converge on some sort of local optimum, assuming we did both steps exactly. And this local optimum is going to be the best possible explanation within some neighborhood of the time series of observations that we saw. So how is this done in practice on a nonlinear system? Well, we use an algorithm called particle EM, or particle expectation maximization. So in order to find the posterior distribution of states given observations, it actually uses something called particle smoothing. And so particle smoothing, so you can see this algorithm essentially in action. So imagine that we are trying to fit the natural frequency of some sort of harmonic oscillator. We call that theta. Imagine we start off at an incorrect guess of 10 theta. So the natural frequency is 10 times larger than it actually is. So the first time you run particle smoothing, you can see that the smooth distributions don't exactly match up with the data, but sort of do. So you can use that smoothing distribution to try to update the model parameters. And over time, the model parameters will start to eventually converge to a good answer or a good guess as to what the natural frequency of the system really is. So while this is a very general algorithm, it is also intractable. So sequential Monte Carlo based approaches tend to suffer from the curse of dimensionality as you scale them to high-dimensional problems. It's also a very unstable algorithm to use. This is because we are using a stochastic approximation to EM as opposed to true EM, and therefore it is a pretty unstable algorithm to work with. So what we ask is, can we stabilize EM as we try to apply it to higher dimensional problems? And we study a methodology called certainty equivalent expectation maximization. So the idea here is to first go back to what particle EM does. It uses sequential Monte Carlo to try to approximate the posterior distribution over those hidden states. So it's got essentially one particle example of a trajectory of what could have been the underlying trajectory explaining the observations that we saw. Right? And so we approximate the posterior distribution as a sum over particles. So instead, what we do over here is say, let's not try to characterize the full posterior. Instead, just look for a single point explanation that is the most likely explanation. So essentially, we're saying if you could choose one particle, what particle would it be? Right? It turns out that in order to find the most likely explanation, we typically just need to run a nonlinear least squares problem. Right? Nonlinear least squares algorithms are both deterministic, typically, and very tractable algorithms that can scale well to higher dimensional problems. So what we get here is tractability. We can scale to higher dimensional problems. It's a deterministic algorithm. It can run quickly, it can run very well. But what we expect to see is some degree of model bias. And this is because we are swapping out the approximate posterior distribution with just a single point. So we're no longer really doing EM. What we're really doing is maximization. And so in our experiments, we try to compare these two algorithms side by side and ask how bad is that bias that we are actually going to encounter, and is it worth using certainty equivalent EM for its performance benefits? We are also going to ask the question about whether certainty equivalent EM can enable us to solve a real-world problem. So let's look at the first question first and study something called a Lorentz attractor. So this is a notorious dynamical system because it has chaotic dynamics. What we are going to do is observe a two-dimensional subspace of this system. And we're going to simulate it with varying degrees of process and observation noise and try to find its three model parameters. Okay, so first let's see certainty equivalent EM in action. Imagine that we simulate it with a bunch of different random seeds incorrectly initialized and given varying amounts of or different trajectories of noisy training data. Right? What we can first see is robust convergence to some sort of local optimum. Okay, and so the true answer is going to be the black dashed line over here. And you can see that almost all initializations tend to converge to close to the right answer. But what we do see is that for at least one of these model parameters, the solutions tend to be converging to a distribution that isn't centered around the right answer. And so this indicates that there is some expected degree of model bias when you use certainty equivalent EM. On the other hand, if we run particle EM, what we first notice is that the convergence is very unstable. So for a lot of these model parameters, it turns out that in the first couple of epochs of running particle EM, we actually diverge from anything like a sensible answer. It's only after you run it for a while that it actually starts to converge to better answers. We can also see that this is a stochastic algorithm introducing some model variance, right? And so the model variance is actually comparable to the model bias that we introduced with certainty equivalent EM. So putting these two algorithms side by side, what we actually see is that certainty equivalent EM is able to find the answers with many fewer epochs than particle EM, and each epoch actually takes about 1/40th the amount of time in order to execute because it is just a much more scalable, tractable algorithm. So what about a higher dimensional system? So over here, what we do is couple many Lorentz attractors together. So in particular, we're going to couple 6 Lorentz attractors together, giving us an 18-dimensional system. So what we expect to see is that as you give the algorithm more and more training data, it is going to converge to a solution that generalizes better and better. And that is exactly what we see for certainty equivalent EM. The more data you get it, the better a solution you get. Also, the more you train it, the better the solution gets, right? So it has monotonic convergence to its optimum. What we see for particle EM is even given the most amount of training data, it actually diverges from its initial guess and converges to a solution that is worse than the initial guess, right? So it's clearly not able to scale to these sorts of high-dimensional problems. So we've shown that certainty equivalent EM does compare favorably with particle EM on the sorts of problems that we compared them on. So now we ask the question, can certainty equivalent EM enable us to solve a real-world problem? So what we're going to look at is a data set collected by Stanford. It was called the Stanford Autonomous Helicopter Project. So this is a helicopter that has been made to do just really impressive maneuvers in the sky. This specific maneuver is called the chaos maneuver. And it turns out that this helicopter is generating a lot of momentum in the fluid around it. And so these are hidden states that we will have to reason about to accurately predict the accelerations or the dynamics of the helicopter. So we ask, can we learn a model of the system despite the hidden states? So even without using certainty equivalent EM, there are a couple of approaches one might try to predict accelerations. So the first is naive regression. So imagine that there weren't any hidden states. We just take the things that we can observe about the system and directly try to predict the accelerations of interest. And we call that naive regression. We would use a neural network to do this because it doesn't reason about hidden states. If you say hidden states to someone in machine learning, they will almost certainly say LSTM back to you. So another thing that we try is to use an LSTM network in order to try to take the time series of observations and use that to predict the acceleration. The state-of-the-art approach for this problem is actually to use an autoregressive model. So we call this the H25 model, and essentially what they do is they use 25 lagged observations of the system in order to try to infer what the next acceleration is going to be. And then from standard control theory, there's an approach called subspace identification, which tries to fit a linear dynamical system to the hidden states and use that to reason about the next acceleration that's coming. So what we do is actually try to fit a nonlinear state space model to the hidden states, and we assume that because we're allowing it to be nonlinear, it can express a larger set of functions, a larger set of descriptions of the hidden state, and hopefully give us the most accuracy. But since we're trying to fit a nonlinear and fairly high-dimensional system to the hidden states, we're going to need to use certainty equivalent EM to fit our approach. So our approach is fit using certainty equivalent EM. The other approaches have much more standard methods that they can be fit with. What we find is, if we compare all of these different approaches to try to fit the dynamics of this helicopter, that our approach actually outperforms in accuracy on a bunch of different test trajectories. It outperforms all of the other approaches. So what we find is that certainty equivalent EM allows us to train a nonlinear state space model that achieves the best accuracy. So the takeaways here are learning nonlinear systems with hidden states requires some form of approximate EM, and certainty equivalent EM is a tractable algorithm that performs well. So now I'm going to quickly touch on some other work that I did, specifically learning reactive models of COVID-19. So everyone on this call knows that COVID-19 has spread unpredictably. We've seen peaks emerge out of nowhere, unpredictably timed and with unpredictable magnitudes. And early in the pandemic, we saw that standard disease models don't capture what we're seeing. Standard disease models typically predict a single sharp peak in infections and a long tail back down to immunity. And this is obviously not what we see. So what we try to do is extend these standard models to make them more expressive. And specifically what we do is we try to allow the infection rate to be predicted using a neural network as a function of the prevalence of the disease and as a function of time. This is a nonlinear system that has hidden states because COVID-19 is partially observed. So as a result, we use certainty equivalent EM in order to fit this system. What we find is that by training this system on a couple of training trajectories from a few counties in the US, the learned model can actually express what happened in a variety of different counties in the United States, much better than the standard approaches can. So this approach is this paper is currently under review at Nature Scientific Reports. Then there is another work that I did on which was a Bayesian approach to safe imitation learning. So over here, we're interested in training AI through shared control. So imagine that you are trying to train a neural network to drive, and so both of you have some partial control over a vehicle. So there is an algorithm called Dagger, which tells you that if you share control between you and the novice policy, the AI that you're training, you will eventually get a data set that is rich enough so that the AI can clone your behavior accurately. But it says that if you want to decide who gets control over the vehicle, just toss a weighted coin. So some share of it you get, some share of it the AI gets. Well, if you're close to a cliff, you surely wouldn't want control of the system to be randomly assigned to a novice that may not know how to deal with that situation. So to consider safety, we actually propose an algorithm called Ensemble Dagger, which fits the novice policy using an ensemble of neural networks, thereby being able to predict its posterior uncertainty. And so using its posterior uncertainty, we can effectively modulate who gets control of the vehicle in a way that is safe and efficient. So we get safe and efficient learning from demonstration, meaning we are able to clone the behavior of the expert without needing to interact with it too much. But we also guarantee better safety than Dagger can guarantee. So this paper was accepted by IROS in 2019. So now I'm going to summarize everything that I talked about and discuss some avenues for future work. So we talked about decision-making systems learned from data. And specifically, we talked about two frameworks, which is the model-based decision-making framework and the model-free decision-making framework. And what we saw is that regardless of the paradigm, there are a common set of challenges. My contributions were in many of these challenge domains. On the question of how to parameterize dynamics models for physical systems, we introduced a physics-informed prior called structured mechanical models that can learn the dynamics of physical systems from limited amounts of data. On the problem of hidden states, we presented a scalable algorithm for identifying partially observed systems called certainty equivalent expectation maximization. On the problem of data acquisition, we studied the problem of safe online learning from demonstration and presented an algorithm called Ensemble Dagger, which tells you how to clone the behavior of an expert. And then we did a case study in a domain with very poor data quality where we learned reactive models of COVID-19. So a couple of future directions for work involve combining the ideas from these various different domains. So we can combine ensembles of neural networks with structured mechanical models to do a true Bayesian analysis of structured mechanical models to actually understand that inductive bias better. Another thing that we can do is try to use structured mechanical models with certainty equivalent EM in order to learn from noisy time series. And this is more than just a trivial application of one algorithm to another, because structured mechanical models can be directly formulated in discrete time, which might be able to give us an added benefit in terms of how efficiently we can learn. I've also been interested in studying imitation learning problems on systems where there are multiple agents interacting with one another, making the overall dynamical system chaotic. And a couple of imitation learning algorithms don't perform that well on chaotic dynamics, but what we've seen is that certainty equivalent EM does perform well on chaotic dynamical systems. So I think it would be interesting to apply certainty equivalent EM to try to stabilize imitation learning. On a longer timescale, I think to enable artificial intelligence, we need to consider the Bayesian identification of each of these models I discussed. Why? Because if we have a Bayesian model, we can do optimal exploration. We can figure out what actions to take next so as to reduce our uncertainty over our model of the world. We can also use it for robust control. So imagine we have a Bayesian model and we put a robot into a safety critical setting. It can use these Bayesian models to choose a sequence of actions that is safe. So I believe that Bayesian identification is going to be key to enabling artificial intelligence. With that, I want to thank you all for the time you've taken to listen to my talk.